Alright, hello, my name is Evan Acosta and this is my Lab 5 video report. I chose the scenario where Felix Baumgartner jumped out of a balloon at an altitude of 120,000 feet. He was the Red Bull athlete that basically jumped from like near the top of the atmosphere and tried to break the speed of sound. So I went ahead and created a model. I just took the skeleton from the first lab and I altered it a bit. So I do have the delta T kind of cranked up, and it also does go longer than he fell just to see like kind of how fast he could be going. Um, so this is what it looks like. It's really fast because my delta T is 1 second. So here you can see that's the velocities and the position um, at the end. So this is higher than what he would have gone. He would have gone to like I think it was one magnitude less. So my final velocity, if he had went this far, is really high. Um, so, first, quick background intro. Obviously, Red Bull athlete Felix Baumgartner was trying to break the sound barrier, and attempting to do so, he jumped from 36,576 meters above the Earth. Using GhostScript, I modeled the free fall as you can see, and I'm just gonna kind of observe it using what we've learned in the class so far. So, the fundamental principles that I used were kinematic equations, so velocity update formula, the position update formula, and those kind of equations, as well as kinetic and potential energy to observe his motion and kind of answer some questions um, about his free fall and some what if questions. So, first, observations. The model matched up with the expected outcome of someone who jumps off a diving board that's 36,000 meters up in the air. He basically just slowly speeds up more and more. However, one thing that my program does not take into account is terminal velocity and, as a result, air resistance. As you can see, it just keeps speeding up forever and ever. It doesn't include a visual representation of terminal velocity. Um, so I was still curious about kind of like the terminal velocity and how fast he actually could go with air resistance taken into account. So I did some research and I found that the average terminal velocity of a person is about 200 kilometers per hour if they're laying flat. And if they dive headfirst, it can go all the way up to 321 kilometers per hour. In the model, at the end of 1,000 seconds, the velocity is in the magnitude of thousands of meters per second, which would be about negative 35,352 kilometers per hour, which is way above the speed of sound. The speed of sound is about like 1.2 kilometers per hour. So, as you can see, my model does extend further and doesn't take into account terminal velocity. So, next we just have some what if questions. So, how tall of a height would Felix have to jump from if he wanted to break the sound barrier? So, Felix, no matter how tall he jumped from, he would never be able to break the sound barrier due to terminal velocity. The velocity needed to break the sound barrier is about 1.2 kilometers per hour, like I said before. The max terminal velocity of the average human is about 320 kilometers per hour. So you can never get above that point because that is the point at which the air resistance, you're moving so fast that the essentially kind of like friction force from the air resistance is um, the same magnitude as the gravity, the acceleration or the force of gravity pushing you downwards. So if Felix didn't open his parachute, what would his final velocity be before he hit the ground? When would he have to open his parachute to stop before he hit the ground? So using the energy principle, I calculated since he only has potential gravitational energy, he had roughly 42 million joules of potential gravitational energy when he's standing at the on top of the board, which is about twice the amount of energy that's imparted by the round fired by a 155 millimeter howitzer gun. And I'm just going to show you guys uh, what a bullet from that looks like because I found this really interesting. Um, so basically, it looks like this. I mean, it's like a mini rocket. So the idea that a single person has that much energy stored within them is really interesting. Um, so I use this energy ignoring air resistance, to find how fast he would have been going using kinetic energy, since by the time he hits the ground, right before he hits the ground, it would all be converted into um, kinetic energy. So he would have been going about 843 meters per second right before he hit the ground, which shows like how much further my model like kind of extends the free fall. And then I looked up the average descent of a parachute, and it's basically just the amount of air resistance that's given over the area of an average parachute, the surface area of it, which is 20 meters, negative 27 meters per second. That's how much it slows people down by. So I calculated it, and given that he was going this fast, he would have had to open his parachute over 30 seconds before he hit the ground, but probably way earlier, like realistically, to avoid a ton of kind of damage. So yeah, that's my lab. If you want more look at my program, that's what it looks like. It's got the velocities on the graphs and position and velocity, and that's pretty much it. Thank you guys for watching.